Think about a magnet on your fridge. You never see it working, but you trust it. Something invisible is pulling, holding, quietly doing its job. Earth has the same kind of invisible force, wrapping around the planet like a protective skin. We live inside it every day and rarely notice. But out there in the universe, this familiar idea goes much further. There are stars where magnetism isn't just a feature, it's their entire identity. Stars so extreme that their invisible pull can tear apart matter itself. They're called magnetars. And tonight, we're going to slowly drift toward one. When you think about stars, it's almost impossible not to think of them as calm and permanent, like quiet lights that have always been there and always will be, rising and setting with a rhythm so steady that it feels reassuring, almost parental, as if the universe itself is keeping watch while you sleep. Stars feel stable because that's how we encounter them, as distant points of light that barely seem to change over a human lifetime, glowing night after night while everything else in our lives moves, ages, and disappears. But stars are not calm, and they are never truly still. They are places of constant struggle, where enormous forces pull in opposite directions without pause, one side trying to tear everything apart while the other side holds everything together. And what we see as gentle light is actually the surface expression of a balance that is always on the verge of failing. A star survives, not because it is peaceful, but because it is locked in a long, delicate stalemate. For most of its life, a star manages this balance well enough. It burns through its fuel slowly, pushing outward just hard enough to resist its own weight, holding itself up against gravity with a kind of quiet endurance that can last for millions or even billions of years, long enough for planets to form, for life to emerge, and for entire histories to unfold beneath its glow. But fuel runs out. It always does. When a star begins to exhaust what keeps it shining, the change does not arrive with drama at first, and there is no sudden announcement that something has gone wrong, only a subtle weakening at the center where the outward pressure starts to lose its grip. Gravity, patient and relentless, senses the shift immediately, and once it begins to win, the process is unstoppable. The star collapses inward, not like a building crumbling or a mountain sliding apart, but in the opposite direction, as everything that once filled an enormous volume of space is forced to occupy less and less room. Layers that were once separated by vast distances slam together. Matter compresses beyond anything we experience on Earth, and the star falls into itself with a speed and intensity that defy everyday intuition. This is where our familiar ideas about size and weight stop behaving the way we expect them to. On Earth, when something collapses, it breaks, spreads, and becomes lighter and looser. But in the universe, collapse often means concentration, as mass is packed tighter and tighter until density reaches levels that feel almost unreal. What remains after this collapse is not a quiet remnant drifting away into darkness, but a neutron star. The dense core left behind after the outer layers of the star are gone, an object so compact that its very existence feels like a contradiction. Imagine taking something heavier than our sun and compressing it into a sphere no wider than a large city, with all that mass held together in a space small enough to fit inside a region you could drive across in an afternoon. This is not a metaphor meant to impress you. It is simply how the universe behaves when gravity is allowed to finish its work. The surface of a neutron star is nothing like rock or metal, because the atoms themselves are no longer arranged in familiar ways, with empty space between them, but are crushed so tightly together that their individual identities begin to blur. Matter becomes something closer to a solid wall of particles, pressed together by forces so strong that even the idea of emptiness nearly disappears. To put it in terms your body can grasp, a tiny fragment of this material, no larger than a spoon, would outweigh a mountain. Not because it is magical or strange, but because gravity has done exactly what gravity always does when it is given enough time and mass to work with. The result is not chaos, but an extreme form of order, where everything is locked into place by pressure beyond comprehension. There is something deeply unsettling about neutron stars, not because they are violent in an obvious way, but because they reveal how fragile our sense of normalcy really is. They show us that the rules we live by are not universal, and that under different conditions, matter itself is willing to behave in ways that feel alien, even hostile to common sense. And yet, even this is still not the furthest the universe is willing to go. Neutron stars are already extreme, but they are not all the same, and the way a star lives before it dies matters deeply to what it becomes afterward. Some stars spin faster, some are born with more internal turbulence, and some carry stronger invisible forces within them from the very beginning. Forces that do not disappear when the star collapses, but instead are dragged inward and intensified. Magnetism, the same quiet influence that guides compasses and protects planets, does not escape the collapse of a star. As the star shrinks, its magnetic field is forced into a smaller and smaller space. And like everything else caught in the collapse, it becomes stronger, tighter, and more concentrated. Imagine stretching an invisible net across a wide field, then pulling it inward until it fits inside a single room, with every thread packed close together, crossing and pulling with far more intensity than before. Nothing new has been added, but everything has changed because the space has disappeared. This is how some neutron stars begin to take on a different identity. They do not simply become dense remnants of dead suns, but objects where magnetism stops being a background feature and starts becoming the defining characteristic, where invisible forces dominate everything else and shape the star's behavior in ways that feel almost aggressive, even though there is no intention behind them. At this stage, the universe has already pushed far beyond what feels reasonable, compressing stars into city-sized objects heavier than planets, turning matter into something barely recognizable, and proving that death does not always mean dispersal or quiet fading. Sometimes, death is an act of tightening, of concentrating power into smaller and smaller forms. What makes this especially difficult to grasp is how small these objects are compared to the power they contain. On a cosmic scale, neutron stars are tiny, almost negligible, and yet they carry within them the mass of stars and the stored energy of unimaginable forces, waiting, stable for now, but always on the edge of further transformation. This mismatch between size and strength is where unease begins to creep in, because it breaks one of the simplest rules we rely on to understand the world, the idea that big things are powerful and small things are harmless. Neutron stars show us that the universe does not respect this rule at all, and that under the right conditions, smallness can hide enormous intensity. And somewhere among these collapsed remnants, among these dense, quiet corpses of once bright stars, there exists a rarer outcome, one that takes everything we have already stretched our imagination to accept and pushes it even further into a realm where magnetism becomes overwhelming and the familiar invisible force from your everyday life turns into something almost unrecognizable. Because some stars do not simply die and settle into dense silence. Some are transformed into objects where magnetism itself takes center stage, reshaping matter, space, and even the way energy is released into the universe. Those stars are called magnetars, and once you understand how a star can collapse into something so small, so heavy, and so extreme, you are finally ready to approach a star where the invisible force you trust without thinking becomes powerful enough to challenge everything you thought you knew about how reality holds together. When we think about stars, we often think of them as something steady and reliable, as distant lights that simply exist without effort, rising and setting with a calm rhythm that feels almost comforting. The sun comes up every morning, warms your skin, then disappears again, and the stars return at night as if nothing has changed. Over a human lifetime, they seem frozen in place, unchanged, and indifferent to time. But a star is never truly calm. Deep inside, far beneath the smooth light you see from afar, it is a place of constant struggle, where enormous forces push and pull against each other without rest. Energy pushes outward, trying to make the star expand, while gravity pulls inward, trying to make everything collapse into a single point. And the light you see is the fragile balance between these two extremes. For most of a star's life, this balance holds. It burns its fuel steadily, turning mass into energy, glowing for millions or even billions of years, depending on its size. Compared to a human life, this timescale feels infinite, long enough that we instinctively treat stars as permanent features of the universe. But even something that burns for billions of years eventually runs out of fuel. When a star begins to exhaust the material that keeps its internal pressure strong, the outward push weakens, and gravity slowly gains the upper hand. The star does not gently fade away. Instead, it begins to lose its structural support. And once that balance tips, gravity pulls everything inward. This collapse is not something we can easily compare to anything on Earth. When buildings collapse or mountains erode, they fall apart and spread out, breaking into smaller and smaller pieces. A collapsing star does the opposite, forcing everything it contains into a smaller and smaller space, compressing matter to densities that feel almost impossible. Imagine taking something larger than the entire solar system and squeezing it down relentlessly, without pause, without mercy. Layer after layer of the star falls inward, heating up as it collapses, until the outer regions crash into the core. The process happens so quickly, on cosmic timescales, that the star barely has time to respond. In some stars, this collapse continues until nothing recognizable remains, leading to an explosion so violent that it briefly outshines entire galaxies. But in others, the collapse stops short of total destruction. What is left behind is the star's core, stripped of its outer layers and crushed into a new form. This remnant is called a neutron star. Despite the name, it is not a faint or gentle object. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers across, roughly the size of a large city. It is small enough that you could drive across it in less than an hour, yet heavy enough to outweigh planets. To understand just how dense this is, it helps to bring the scale back to something your body can imagine. A single spoonful of neutron star material would weigh billions of tons, roughly the mass of a mountain. Not because it is made of anything unfamiliar, but because there is almost no empty space inside it. The atoms are squeezed together so tightly that their usual structure begins to collapse. On Earth, most of what we call solid is actually empty space, with electrons orbiting nuclei at vast distances relative to their size. In a neutron star, that space is gone. Pressure becomes so extreme that electrons are forced into protons, creating neutrons, and matter settles into a state that exists nowhere else naturally in the universe. If you could somehow stand on the surface of a neutron star, gravity would be so strong that your body would be flattened instantly, pulled downward with a force billions of times stronger than what you feel on Earth. Even light would struggle to escape, bending under the star's gravity before finally breaking free. Many neutron stars spin at incredible speeds, some rotating hundreds of times per second, faster than the blades of a helicopter or the turbines of a power plant. This rapid rotation is a leftover from the original star's spin, conserved as the star collapses, much like a figure skater spinning faster when they pull their arms inward. Despite their intensity, most neutron stars live relatively quiet lives. They cool slowly, radiating away their remaining energy over millions of years, fading into the background of the galaxy as dense, compact relics of something once much larger. They are extreme, but they are still understandable within the rules we expect. But some neutron stars are born with an additional trait that changes everything. Along with their mass and spin, they inherit a magnetic field from their parent star. And when that star collapses, the magnetic field collapses with it. Magnetism is one of those forces that feels familiar precisely because it is usually so gentle. It guides a compass needle toward north, helps protect Earth from harmful radiation, and allows electric motors and generators to function quietly in the background of modern life. You rarely notice it unless something goes wrong. Earth's magnetic field stretches tens of thousands of kilometers into space, forming a protective bubble that shields the planet from the solar wind. Even so, it is weak enough that you can live your entire life without ever feeling it directly, unaware that it is constantly shaping the environment around you. When a star collapses into a neutron star, that magnetic field is suddenly squeezed into an object no larger than a city. The same invisible force that once filled an enormous volume of space is now concentrated into a tiny region. The result is a magnetic field that becomes almost unimaginably strong. In most neutron stars, this magnetic field is already millions of times stronger than Earth's, but in a small number of cases, the field grows even stronger, reaching levels thousands of trillions of times greater than the magnetic field that surrounds our planet. At this point, magnetism stops being a background force and becomes the defining feature of the star. These objects are known as magnetars. The name is simple, combining magnet and star, but it barely captures how extreme they are. A magnetar is not just a neutron star with a strong magnetic field. It is a star where magnetism dominates everything else. To understand how powerful this magnetism is, consider something ordinary, like a credit card. The magnetic strip on the back stores information in tiny magnetic domains. Near a magnetar, the magnetic field would be strong enough to erase that data from a distance comparable to the space between Earth and the Moon, without ever touching the card. Metal objects would not need to be close to feel its influence. Even from far away, the magnetic field of a magnetar could cause metal to vibrate or twist, responding to forces far stronger than anything produced by human technology. Electronics would fail instantly, overwhelmed by the invisible pressure. But the most unsettling effects happen at even smaller scales. Near a magnetar, the magnetic field becomes so intense that it can distort the structure of atoms themselves. The usual rules that govern how electrons move around nuclei begin to break down, and matter behaves in ways that feel deeply unfamiliar. The surface of a magnetar is unlike anything else in the universe. It is thought to be incredibly rigid, stronger than steel or diamond, not because it is made of some special material, but because gravity and magnetism work together to lock everything in place. When stress builds up on this surface, it does not crack gently. Instead, the surface can fracture in events sometimes described as starquakes, releasing enormous amounts of energy in a fraction of a second. These releases can send powerful bursts of radiation racing across space, detectable from vast distances, even across entire galaxies. What makes this remarkable is not just the amount of energy released, but how far its influence can reach. Events on a magnetar, happening on an object smaller than a city, can be felt across tens of thousands of light years, briefly affecting the space around Earth despite the immense distance. There is something unsettling about this mismatch between size and power. A magnetar is tiny by cosmic standards, easy to overlook in a galaxy filled with hundreds of billions of stars, and yet it is capable of influencing space far beyond its immediate surroundings. Its invisible field extending its reach across unimaginable distances. Unlike stars that shine brightly and announce their presence through light, magnetars can be quiet for long periods of time. They may sit in darkness, slowly rotating, their immense power hidden beneath a calm exterior. From afar, they do not look threatening or dramatic. This quietness is part of what makes them unsettling. The most extreme forces in the universe are not always loud or obvious. Sometimes they exist in silence, storing energy, shaping their surroundings invisibly, waiting for moments when that energy is suddenly released. There is also something strangely familiar in this pattern. We tend to associate danger with size, noise, and motion, assuming that the biggest and brightest things are the most powerful. Magnetars challenge that instinct, showing that concentration can be just as important as scale. In human terms, it is like finding that something small and unassuming holds more power than something vast and impressive. A single thought can change a life, a quiet decision can alter history, and an invisible force can shape an entire world without ever being seen. The universe seems to favor this kind of intensity. It does not always spread energy out evenly or gently. Sometimes it gathers it, compresses it, and focuses it into places so extreme that they challenge our understanding of reality. Magnetars are a reminder that the universe does not need to be large to be powerful, or bright to be dangerous. They are the end result of stars pushed beyond their limits, where gravity, pressure, and magnetism combine into something that feels almost unreal. As you hold this image, a small, dense star quietly spinning somewhere in the galaxy, wrapped in a magnetic field strong enough to reshape matter itself, it becomes clear that the familiar forces of everyday life have far more extreme expressions than we ever encounter. The same magnetism that gently holds a piece of paper to your fridge can, under the right conditions, dominate a star, twist atoms, and send signals across the galaxy. The difference is not the nature of the force, but how far it has been pushed. And somewhere in that realization, the universe begins to feel both more dangerous and more fascinating, revealing that the ordinary and the extreme are not separate categories, but points along the same continuous spectrum. If you stop and think about magnetism in your daily life, it feels almost disappointingly small. A compass needle turning north, a train gliding along invisible tracks, a magnet holding a note to a fridge door without effort or sound. It is a force that works quietly, politely, never demanding your attention, and most of the time you forget it exists at all. Earth's magnetic field is like that. It surrounds the planet, stretching far into space, deflecting harmful particles from the sun and guiding birds across oceans. Yet you never feel it on your skin. You can live your entire life inside it without sensing its presence, the same way you live inside air without constantly thinking about breathing. Now, imagine taking that invisible field and slowly turning a dial. Not a little bit, but far beyond anything you would ever encounter on Earth. Strong enough that compasses no longer behave, strong enough that electronics struggle, strong enough that magnetism stops being background noise and starts becoming the main force, shaping everything around it. This is where magnetars live. A magnetar is not a different kind of star in the way a red star differs from a blue one. It is a neutron star that has taken one familiar force and pushed it to an extreme. The star itself is still only about 20 kilometers across, roughly the size of a city, but its magnetic field is so strong that it dominates the space around it in ways that feel almost unreal. To understand how extreme this is, it helps to start with Earth. The magnetic field around our planet measures less than 1 Gauss, a unit so small it rarely matters outside of physics textbooks. A typical refrigerator magnet is a few hundred Gauss, strong enough to hold paper but weak enough that you can pull it away with 2 fingers. A magnetar's magnetic field reaches values around 1,000 trillion Gauss. Written out, the number looks abstract, but the meaning is simpler. It is the strongest magnetic field we know of in the universe. There is nothing humans can build, no laboratory, no machine, that comes even remotely close. At this strength, magnetism stops behaving like the gentle force you are used to. Near a magnetar, the magnetic field is so intense that it can erase the data on a credit card from a distance comparable to the space between Earth and the Moon, roughly 400,000 kilometers, without ever touching it. The tiny magnetic domains that store information simply cannot hold their pattern anymore. Metal objects would not need to be nearby to react. Even from far away, the field could cause metal to vibrate or twist, responding to invisible forces, pulling and pushing at the atomic level. Electronics would fail instantly, overwhelmed by currents induced by the shifting magnetic environment. But these effects, dramatic as they sound, are still surface level. The truly strange behavior begins when magnetism becomes strong enough to interfere with matter itself. At extreme field strengths, the way electrons move around atoms begins to change, and the familiar structure of matter starts to distort. On Earth, atoms are mostly empty space, with electrons moving in clouds around a dense nucleus. Near a magnetar, the magnetic field forces those electrons into tight, elongated paths, squeezing atoms into shapes they were never meant to have. Matter becomes stretched, compressed, and altered simply by existing in that environment. The surface of a magnetar reflects this extremity. It is thought to be incredibly rigid, stronger than steel or diamond, not because it is made of some special substance, but because gravity and magnetism work together to lock everything into place. The crust behaves less like rock and more like a single, strained structure under enormous stress. Over time, that stress builds. The magnetic field slowly shifts, tugging at the star's surface, pulling and twisting it the way tectonic forces pull at Earth's crust. But unlike Earth, where rock can slowly bend and release pressure, a magnetar's crust resists until it can no longer hold. When it finally fractures, the result is a starquake. In less than a second, the magnetar releases an enormous amount of energy, sending a burst of radiation racing outward through space. These bursts are so powerful that they can be detected across tens of thousands of light years, even when they come from an object smaller than a city. One such event, observed in the early 2000s, briefly altered Earth's upper atmosphere despite originating from a magnetar located tens of thousands of light years away. Instruments in orbit registered a sudden spike, not because Earth was in danger, but because the energy was simply that intense. To put this into perspective, imagine a small crack forming in the surface of a city-sized object, and that crack releasing more energy in a fraction of a second than our sun emits over hundreds of thousands of years. The scale mismatch feels wrong, as if something that small should not be capable of something that large. This is a recurring theme with magnetars. They are compact, almost insignificant in size compared to stars or galaxies, yet their influence can stretch across vast distances. Power, in this case, has nothing to do with being large and everything to do with being concentrated. Most of the time, magnetars are quiet. They do not shine brightly like ordinary stars, and they do not constantly announce their presence. They spin slowly, sometimes taking several seconds to complete a single rotation, and gradually lose energy over time. This quietness is deceptive. It is the calm of something under tension, storing energy rather than releasing it. Like a tightly wound spring, the magnetar holds its power invisibly, waiting for moments when that tension suddenly breaks. What makes magnetars especially unsettling is how familiar their building blocks are. Magnetism is not an exotic force invented for extreme stars. It is the same phenomenon that allows electric motors to work and compasses to point north. The difference is not in kind, but in degree. The universe has taken a force you experience casually and amplified it beyond recognition. It is like turning up the volume on a whisper until it becomes a roar, not by changing what it is, but by pushing it far past the limits you are used to. This idea challenges a common instinct about the universe. We often assume that the most dangerous or powerful things must be visibly dramatic, massive, or fast-moving. Magnetars undermine that assumption, showing that stillness and concentration can be just as extreme. A magnetar does not need to explode constantly to be dangerous. Its mere existence reshapes the space around it. Charged particles are trapped and guided by its magnetic field, forming structures that would be impossible elsewhere. Light itself behaves differently, bending and scattering under the influence of the field. There is also something deeply humbling about the fact that magnetars exist at all. They are not theoretical curiosities or rare accidents. They are natural outcomes of stellar evolution. When certain stars are born with the right conditions, magnetars are simply what happens next. This suggests that the universe is comfortable creating objects that sit far outside human intuition. It does not stop at what feels reasonable or safe. It follows its rules wherever they lead, even when the results feel extreme or unsettling to us. Despite their power, magnetars are rare. In a galaxy containing hundreds of billions of stars, only a few dozen are thought to exist. Their rarity adds to their mystique, making each one feel like a singular experiment carried out by the universe itself. Yet even in their rarity, they remind us that the familiar and the extreme are connected. The same magnetism that quietly protects Earth can, under different conditions, dominate a star and distort matter. The difference lies not in the force itself, but in how tightly it has been compressed. It is tempting to imagine magnetars as cosmic monsters, but they are not malicious. They do not seek destruction, and they are not aware of anything beyond their immediate environment. They simply exist, following the same physical laws as everything else, pushed to their most intense expression. There is something oddly reassuring in that. The universe does not create extremes out of cruelty or intention. It creates them because it can, because its rules allow it, and because there is no reason for it to stop before reaching those limits. As you hold the idea of a magnetar in your mind, a small, dense star wrapped in a magnetic field strong enough to reshape atoms, it becomes harder to think of magnetism as a minor detail of reality. It is a fundamental force, capable of both subtle guidance and overwhelming dominance. The invisible pull that feels so gentle in your daily life is part of the same continuum that leads to these extreme stars. There is no sharp boundary between ordinary and extraordinary, only a gradual increase in intensity as conditions change. Somewhere in the galaxy, magnetars spin quietly, their power hidden beneath a calm exterior, reminding us that the universe often saves its most extreme expressions for places we rarely look. They are proof that reality has depths far beyond what we experience directly. And once you accept that, once you see how something so familiar can become so overwhelming, it becomes easier to let go of the idea that the universe must make sense on human terms. It does not exist to be comfortable or intuitive. It exists to explore what is possible. And magnetars are one of the clearest signs of how far that exploration can go. We usually think of matter as something dependable. The floor feels solid under your feet, a table resists your hands when you lean on it, and your own body feels like a stable shape that belongs to you. Even when things break, they still follow familiar rules, turning into pieces, dust, or fragments that remain recognizably physical. This sense of solidity is so deeply ingrained that it feels universal, as if matter itself has agreed to behave this way everywhere. We trust that atoms will keep their structure, that objects will keep their form, and that reality will not suddenly change its texture. Most of the time, that trust is rewarded. Near a magnetar, that trust quietly begins to fail. Matter does not disappear or dissolve, but it starts to behave in ways that no longer match everyday experience. The forces involved become so strong that the basic assumptions you carry about how things hold together begin to loosen, then bend, and finally give way. On Earth, atoms are mostly empty space. If you could remove that emptiness, the solid objects around you would shrink to almost nothing. Electrons move around nuclei at distances that feel enormous compared to their size, and this empty space is what gives matter its familiar softness and flexibility. Near a magnetar, the magnetic field is so intense that it interferes directly with how electrons move. Instead of orbiting freely, electrons are forced into narrow paths, squeezed into alignment by the overwhelming magnetic pressure. Atoms lose their usual round, balanced shape and stretch into elongated forms, like tiny strands pulled tight. To imagine this, think about iron filings sprinkled near a magnet. Instead of lying randomly, they snap into ordered lines, responding instantly to the invisible force beneath them. Near a magnetar, something similar happens, but at the level of atoms themselves, with matter reorganizing simply because magnetism demands it. This distortion does not stay confined to individual atoms. As the structure of atoms changes, the behavior of matter as a whole begins to change with it. Materials that would normally bend or crack respond differently, becoming rigid in some directions and strangely fragile in others. The surface of a magnetar is one of the most extreme examples of this effect. It is often described as a crust, but that word barely does it justice. This crust is thought to be billions of times stronger than steel, not because it is made of some special cosmic substance, but because gravity and magnetism together lock everything into place. Gravity presses downward with unimaginable force, while magnetism holds particles in tight, ordered arrangements. The result is a surface that behaves less like rock and more like a single, stressed structure, stretched to its limits and resisting change with immense strength. But even this strength has a breaking point. As a magnetar slowly evolves, its magnetic field shifts and rearranges itself. These changes happen over years or centuries, far too slowly to notice directly, but they place increasing strain on the star's rigid surface. The crust is pulled and twisted, much like Earth's tectonic plates are stressed by forces deep below the surface. On Earth, when stress builds up in the crust, it is often released gradually through small movements, or, occasionally, through earthquakes. Even the largest earthquakes, powerful as they are, release energy that feels enormous only because our planet is small and our structures are fragile. On a magnetar, the situation is very different. When the crust finally gives way, the fracture happens across a surface under pressures far beyond anything found on Earth. The release is sudden, violent, and brief, lasting less than a second, yet releasing more energy than our sun emits over hundreds of thousands of years. These events are known as starquakes, and they are among the most energetic occurrences in the universe. The energy released does not come from motion or collision, but from the sudden rearrangement of magnetic and structural stress, snapping into a new configuration. In the early 2000s, astronomers observed one such event from a magnetar located roughly 50,000 light-years away. Despite this enormous distance, instruments near Earth registered a powerful burst of radiation, strong enough to briefly affect the upper layers of our atmosphere. To put that distance into perspective, 50,000 light-years means the signal began its journey long before human civilization existed, traveling across the galaxy before finally brushing past our planet. And yet, when it arrived, it was still strong enough to be noticed. This is where the scale becomes deeply unsettling. An object smaller than a city experiences a crack in its surface, and that crack releases energy that remains measurable after crossing tens of thousands of light-years. Size, in this environment, no longer tells you anything about impact. What travels outward from these starquakes is not sound or visible light, but intense radiation, including gamma rays, the most energetic form of light known. Gamma rays are so powerful that they can pass through solid objects and disrupt biological tissue. Yet in this case, distance dilutes their danger long before they reach us. Even so, the fact that Earth can register such an event at all is a reminder that space is not as empty or disconnected as it feels. Extreme events echo across vast distances, leaving faint but detectable traces long after they occur. Near the magnetar itself, the environment becomes almost impossible to imagine. Magnetic fields twist space around the star, trapping charged particles and guiding them along invisible lines. Light behaves differently, scattering and bending in ways that feel unnatural compared to everyday experience. Matter in this region exists under constant strain. Atoms are distorted. Particles are forced into unnatural arrangements, and the familiar boundaries between solid, liquid, and gas lose their meaning. Everything is held together not by comfort or balance, but by overwhelming force. It is tempting to think of this as chaos, but it is not random. The behavior of matter near a magnetar follows precise rules, even if those rules operate far outside the range of human intuition. The same physical laws apply, but they are pushed to extremes where their consequences feel alien. There is something humbling about realizing that matter itself has limits. We often treat the physical world as a reliable foundation, something that can always be counted on to behave predictably. Magnetars show that this reliability depends entirely on context. Under enough pressure and force, matter does not disappear, but it stops behaving in ways we recognize. It becomes something else, still physical, still real, but no longer comfortable or familiar. This realization carries a quiet lesson. The universe does not guarantee stability. It offers conditions, and within those conditions, things behave accordingly. When the conditions change enough, even the most basic assumptions give way. And yet, even in these extreme environments, there is a strange kind of order. Magnetars do not destroy matter indiscriminately. They reshape it, constrain it, and force it into new configurations dictated by overwhelming fields and gravity. From a distance, all of this is invisible. A magnetar does not look dramatic in ordinary light. It does not blaze like a supernova or glow like a young star. Most of the time, it appears as a faint point, easy to overlook among billions of others. This contrast between appearance and reality is part of what makes magnetars so unsettling. The most extreme behavior is hidden beneath a calm exterior, revealed only through rare bursts or subtle signals picked up by distant instruments. It also challenges the way we instinctively judge danger and power. We are used to associating threat with movement, noise, and size. Magnetars demonstrate that stillness and concentration can be just as extreme, if not more so. The idea that matter itself can be bent, stretched, and rearranged simply by existing near an object is difficult to fully accept. It forces a re-evaluation of what solidity really means, and how fragile our everyday experience of reality actually is. In a sense, magnetars act as stress tests for the universe. They push matter, energy, and physical laws to their limits, revealing how they behave when comfort and balance are no longer options. This does not mean that matter is weak. On the contrary, it shows how resilient matter can be, holding together under conditions that feel impossible. But it also shows that resilience has boundaries, beyond which new behaviors emerge. As you sit with this idea, the world around you may feel slightly different. The chair beneath you, the walls around you, your own body, all feel solid and dependable. And they are, within the gentle conditions of Earth, somewhere else in the universe, under far harsher conditions. Those same building blocks are being twisted into unfamiliar shapes, stretched and compressed by forces that make everyday reality seem almost fragile. This contrast does not diminish the value of the ordinary. If anything, it highlights how special and balanced our environment is. Stability is not guaranteed everywhere. It is a condition that exists only when forces are in the right proportion. Magnetars remind us that the universe is capable of far more extreme expressions than we usually encounter. They reveal that the solid world we rely on is just one version of reality, shaped by a narrow range of conditions. And once you accept that matter itself can give up its familiar behavior, it becomes easier to let go of the idea that the universe must always feel comfortable or intuitive. It does not exist to protect our expectations. It exists to explore what happens when its rules are pushed to their limits, and magnetars are one of the places where that exploration becomes impossible to ignore. Most of the time, magnetars are quiet. They sit in the darkness of space, rotating slowly, barely noticeable against the background of countless other stars. If you were watching from far away, nothing about them would suggest violence or drama, only a faint, steady presence that seems almost peaceful. This quietness can last for years or even centuries. During these long stretches, a magnetar does not announce itself, does not flare brightly, and does not demand attention. Its immense power remains stored, locked inside magnetic fields so strong that they hold everything in place, waiting. But when that balance finally breaks, the universe does not whisper. When a magnetar releases energy, it does so suddenly and without warning. The event does not produce sound in the way we understand it, because sound needs air to travel, and space is almost entirely empty. What it releases instead is a burst of radiation so intense that, if sound could travel through space, it would feel like a scream. These outbursts are known as giant flares, and they are among the most powerful explosions ever observed since the birth of the universe. In a fraction of a second, a magnetar can release more energy than our sun emits over hundreds of thousands of years, all concentrated into a brief, violent pulse. One such flare was observed in December of the early 2000s, coming from a magnetar located roughly 50,000 light-years away, on the opposite side of our galaxy. That distance is so vast that light from the event began its journey long before humans built cities or recorded history. And yet, when the radiation finally reached Earth, it was still strong enough to overwhelm satellites and trigger detectors designed to monitor distant cosmic explosions. Some instruments were temporarily blinded, not because Earth was in danger, but because the signal was simply too intense to ignore. To put that into everyday terms, imagine a single crack forming on the surface of an object no larger than a city, and that crack releasing enough energy to be noticed across an entire galaxy. It is like striking a match and having its flash detected from another continent, even after traveling for decades. The initial burst from a giant flare lasts less than a second, but its effects ripple outward. Gamma rays, the most energetic form of light, race across space at the speed of light, carrying with them a signature so distinct that astronomers can immediately tell it did not come from an ordinary star. Gamma rays are not light you can see. but they are light nonetheless, carrying immense energy in each particle. On Earth, gamma rays are associated with radioactive materials and medical treatments, and even small doses are handled with care. A giant flare releases more gamma radiation in a heartbeat than our planet encounters over many lifetimes. Despite this, Earth remains safe because of distance. By the time the radiation reaches us, it has spread out, its intensity diluted across unimaginable volumes of space. What arrives is only a faint echo of the original event, strong enough to measure, but not strong enough to harm. This balance between extreme power and vast distance is one of the defining features of the universe. It allows events of incredible violence to occur without turning the cosmos into a place of constant destruction. Space is large enough to absorb even the most dramatic outbursts. Near the magnetar itself, however, the environment is anything but gentle. The sudden release of energy rearranges magnetic fields, accelerates particles to near-light speeds, and floods the surrounding region with radiation. For anything nearby, there is no warning and no escape. What makes these flares especially unsettling is how rare and unpredictable they are. A magnetar may remain quiet for decades, giving no hint of what it is capable of, and then release a burst so powerful that it briefly becomes one of the brightest sources of energy in the entire galaxy. This unpredictability challenges our instinct to look for patterns and schedules. We are used to thinking in terms of cycles and regularity, of cause and effect unfolding in understandable ways. Magnetars remind us that some of the universe's most extreme events do not follow rhythms we can easily anticipate. There is also something deeply humbling about the fact that we can detect these events at all. The radiation from a giant flare travels across tens of thousands of light years, passing through empty space, dust clouds, and star systems, before finally brushing past our planet. By the time it reaches Earth, it carries with it a story written long ago, a message from a distant corner of the galaxy that arrives without caring whether anyone is listening. And yet, we are listening. Our instruments, orbiting quietly above the atmosphere or resting on the ground, are sensitive enough to register these faint echoes. They translate invisible signals into data, allowing us to reconstruct events that happened far beyond our reach. In this sense, humanity occupies a strange position. We are small, fragile, and confined to a single planet, yet capable of perceiving events that dwarf our entire history in scale and energy. We cannot influence magnetars, and they do not notice us, but there is a connection all the same. The radiation that reaches Earth from a giant flare does not feel like a scream by the time it arrives. It is more like a distant vibration, a subtle disturbance that instruments notice long before human senses ever could. But knowing what produced it gives the event a weight that numbers alone cannot convey. It means that something smaller than a city, located halfway across the galaxy, briefly outshone almost everything else in the universe. It means that forces capable of reshaping matter and space exist quietly, releasing their energy only on rare occasions. There is also something unsettling about how quickly these flares happen. In less than a second, more energy is released than the sun produces over a time span longer than human civilization has existed. The timescales do not match our intuition, making it difficult to emotionally grasp what has occurred. We tend to associate great power with long build-up and prolonged display, assuming that something extraordinary must take time. Magnetars break that expectation, showing that the most dramatic changes can happen almost instantaneously. After a giant flare, the magnetar often returns to silence. The radiation fades, the magnetic field settles into a new configuration, and the star continues spinning as if nothing remarkable has happened. From the outside, there may be no obvious sign that such an extreme event has just occurred. This return to quiet is perhaps the most unsettling part. It suggests that the universe does not dwell on its own extremes. It releases energy, reshapes itself, and then moves on without pause or reflection. For us, the event remains extraordinary. We catalogue it, study it, and try to understand what it tells us about the limits of physics. For the magnetar, it is simply another adjustment, another way of relieving internal stress. There is a strange parallel here with natural disasters on Earth. An earthquake can reshape landscapes and alter lives in moments. Yet the planet continues rotating, weather patterns continue, and life goes on. The event is catastrophic to those affected, but insignificant to the larger system. Magnetar flares are like earthquakes on a cosmic scale, releasing built-up tension in sudden, violent bursts. The difference is that their reach extends across the galaxy, and their energy dwarfs anything our planet can produce. And yet, even with all this power, magnetars are not agents of destruction in the way we often imagine cosmic threats. They do not roam the galaxy, seeking to wipe out worlds. They are fixed in place, bound by gravity, acting only within their immediate surroundings. Distance protects us. Space itself acts as a buffer, ensuring that even the loudest screams of the universe arrive at our doorstep as whispers. This vastness is not empty or meaningless. It is what makes existence possible. Knowing this changes the way the universe feels. It is no longer just a cold, silent expanse, but a place where extreme events occur regularly, their echoes traveling for ages before gently brushing against distant worlds. Somewhere out there, magnetars continue their quiet rotation, storing energy, releasing it in rare and violent moments, then returning to stillness. Their screams race across the galaxy, fading slowly as they go. And here, on a small planet orbiting an ordinary star, we catch those echoes, not because they were meant for us, but because the universe is connected in ways that allow even the most distant events to be felt. That connection does not make us important in a cosmic sense, but it does make us participants, listeners, in a universe that occasionally raises its voice. Magnetars are not evil, and they are not angry. They do not exist to destroy, and they do not know that anything else exists at all. They spin, they store energy, they release it when the internal balance shifts, and then they return to silence, following the same physical rules as everything else in the universe. This can feel unsettling at first, because we are used to assigning intention to powerful things. Storms feel angry, fires feel destructive, and earthquakes feel cruel because of the damage they cause. But magnetars do not act with intention, and the universe does not aim its forces at anyone in particular. The radiation from a magnetar flare does not travel outward with a target in mind. It spreads in all directions, thinning out as it goes, indifferent to whether it ever reaches a planet, a star, or nothing at all. Earth is not special for being touched by these echoes. It is simply in the way. This indifference is one of the hardest ideas to sit with. The universe does not care whether we exist, whether we are watching, or whether we understand what is happening. Magnetars were forming, flaring, and fading long before humans appeared, and they will continue long after we are gone. And yet, this lack of concern is not the same as hostility. The universe is not working against us. It is simply not working for us either. It follows its rules with complete consistency, allowing stars to form, collapse, and transform without regard for what those processes might mean to life elsewhere. When a magnetar releases a giant flare, the event is not a message or a warning. It is simply the result of magnetic stress being released, like a tightly wound spring snapping into a new position. The energy has to go somewhere, and space is where it goes. From a human perspective, the numbers involved are overwhelming. A single magnetar flare can release as much energy in a second as our sun emits over hundreds of thousands of years, a comparison so extreme that it almost loses meaning. But from the universe's perspective, it is just energy changing form. This shift in perspective can feel uncomfortable, because it removes humanity from the center of the story. We are not the audience the universe is performing for, and we are not the reason these extreme objects exist. They are simply what happens when gravity, pressure, and magnetism are pushed far enough. There is a strange freedom in this realization. If the universe is not watching us, judging us, or designing itself around us, then our existence does not need cosmic permission. We are not here because the universe wanted us. We are here because the conditions allowed us. Magnetars make this especially clear. They are so extreme, so far removed from anything we can survive, that they highlight how narrow the range of conditions is that allows life to exist at all. The same universe that creates magnetars also creates gentle planets, liquid water, and stable climates. This contrast is not accidental. It is the result of vastness. In a universe large enough, every possibility that the rules allow will eventually occur. Magnetars are one expression of those rules, pushed to their limits, just as calm, life-friendly environments are another. It is easy to look at objects like magnetars and feel small, even insignificant. Compared to something that can release more energy in a second than our sun does over hundreds of millennia, human achievements can feel fragile and temporary. Our cities, technologies, and histories seem tiny by comparison. But small does not mean meaningless. A whisper is small compared to a thunderclap, yet it can still carry information, comfort, or truth. A single human life is small on cosmic scales, but it is complete on its own terms, experienced from the inside, moment by moment. The universe does not assign value based on size or power. It does not rank stars, planets, or people. Value is something that emerges locally, from experience, from consciousness, from the ability to feel and reflect. Magnetars, for all their power, do not experience anything. They do not wonder about their place in the galaxy or reflect on the forces that shape them. They simply exist, following the paths laid out by physics, incapable of noticing their own extremity. We, on the other hand, can notice. We can receive faint signals from across the galaxy, reconstruct events that happened tens of thousands of years ago, and imagine objects we will never touch. That ability does not make us important to the universe, but it does make the universe meaningful to us. There is something quietly profound about the fact that a creature living on a small planet around an ordinary star can understand magnetars at all. The same laws that govern those distant stars also govern the chemistry in your body and the electricity in your brain. This continuity matters. It means that the universe is not divided into a familiar, human-friendly part and an alien, unreachable part. It is one connected system, operating under the same principles everywhere, from your kitchen to the far side of the galaxy. Magnetars remind us that those principles do not adjust themselves for comfort. They produce outcomes that range from gentle to extreme, from life-sustaining to utterly inhospitable. The universe does not aim for balance. Balance simply emerges in certain places for certain lengths of time. Seen this way, Earth begins to feel less like a default setting and more like a rare arrangement. The calm magnetic field that protects our planet, the moderate gravity that lets us stand upright, the stable sun that shines steadily for billions of years, all exist within a narrow window. Magnetars exist outside that window, showing what happens when conditions drift far from what life requires. They are not warnings or mistakes. They are demonstrations of how flexible and far-reaching physical laws can be. This perspective can change how you think about safety and fragility. Life is not guaranteed by the universe. It is permitted by it, allowed to exist where circumstances happen to line up. That permission does not come with promises or protections beyond what physics naturally provides. And yet, here we are, living inside that permission, breathing, thinking, and listening to stories about stars that could never host us. The universe does not care whether we exist, but it has created a place where we can. There is a quiet beauty in that indifference. If the universe were designed for us, our existence might feel expected, even inevitable. Instead, it feels contingent, precious, and improbable. The result of countless conditions aligning for a brief moment in cosmic time. Magnetars help sharpen that feeling. They show us what the universe is capable of when it is unconstrained by the needs of life, when it follows its rules to their most extreme conclusions. Against that backdrop, the gentleness of our environment stands out more clearly. This does not mean we should feel afraid or insignificant. It means that meaning is not handed down from the cosmos. It is created locally, through experience and awareness. The universe provides the stage, but it does not write the script. Understanding magnetars does not make them less extreme or less alien. Instead, it places them in context as one part of a vast system that produces both destruction and stability without preference. The same laws that tear matter apart near a magnetar also allow atoms to form molecules and molecules to form living cells. This connection can feel comforting, even soothing. It suggests that the universe is not chaotic or hostile, but consistent, even when its outcomes feel overwhelming. Magnetars are not exceptions to the rules, they are expressions of them. As you think about this, the universe may start to feel less like an enemy and more like an indifferent landscape, vast and varied, containing cliffs, valleys, storms, and calm seas. Some regions are deadly, others nurturing, and none are arranged with intention. In such a landscape, finding a place to stand becomes meaningful. Stability is not guaranteed everywhere, so where it exists, it matters. Calm is not universal, so when it appears, it is worth noticing. Magnetars, with all their power, do not diminish the value of quiet moments. If anything, they highlight how rare and delicate those moments are. Against a backdrop of extreme forces, gentleness becomes something remarkable. The universe does not care, but that does not mean it is empty of beauty. Beauty emerges in the contrast between extremes, in the coexistence of violence and calm, power and subtlety, vastness and intimacy. And perhaps that is the most important thing magnetars have to offer, not as objects of fear, but as reminders that meaning does not come from being central or powerful. It comes from being aware, from noticing where you are, and from understanding how rare and balanced that place truly is. After thinking about magnetars, about stars crushed into city-sized remnants and magnetic fields strong enough to reshape matter, it helps to let your attention drift back inward, away from distant galaxies, away from extreme forces, back to the place where you are right now. A room, a bed, a chair, the quiet presence of your own body. You can feel the surface beneath you, supporting your weight, solid and reliable in a way that now feels slightly more remarkable than it did before. Gravity here is gentle, just strong enough to keep you grounded without pinning you down. Nothing is being crushed, stretched, or distorted beyond recognition. Your breath moves in and out without effort. Air fills your lungs, then leaves again, following rhythms that your body learned long before you were aware of them. Each breath is shaped by gravity, pressure, and temperature, the same basic forces that shape stars. But here, they exist in a narrow, forgiving balance. It is easy to forget how specific this balance is. Earth's gravity is strong enough to hold an atmosphere, but not so strong that it flattens you. The planet's magnetic field is powerful enough to shield life from harmful radiation, but gentle enough that it goes unnoticed. The sun is massive and energetic, yet steady, shining for billions of years without sudden, catastrophic changes. Compared to magnetars, all of this feels almost fragile, and in a sense, it is. The conditions that allow you to exist are not guaranteed by the universe. They are the result of circumstances lining up in a very particular way. A slightly stronger gravity, a slightly more violent star, a wildly different magnetic field, and this moment would not be possible. And yet, here you are. The same universe that creates magnetars also creates places calm enough for sleep. It follows the same rules everywhere, but those rules produce very different outcomes depending on where and how they are applied. Extreme compression leads to magnetars, while gentle balance leads to oceans, forests, and breathing bodies. There is something quietly grounding about realizing that you are not separate from this system. The atoms in your body were formed in stars long before Earth existed. The iron in your blood, the calcium in your bones, all come from ancient stellar processes that once looked nothing like life. Those stars lived, burned, collapsed, and transformed, contributing their material to future generations of stars and planets. Over vast stretches of time, that material found its way into this planet, into ecosystems, into food, and eventually into you. The connection is not symbolic. It is literal. Magnetars represent one extreme of that stellar story, where matter and energy are pushed so far that life cannot follow. You represent another outcome, where the same ingredients are arranged gently enough to think, feel, and wonder. Both are valid expressions of the same universe. It is tempting to compare these outcomes and feel small. Compared to objects that can release more energy in a second than our sun does over hundreds of thousands of years, a human life seems brief and delicate. Our concerns, routines, and quiet moments can feel insignificant against such vastness. But scale is not the same as meaning. A magnetar does not experience anything. It does not notice its own power or reflect on its place in the galaxy. It does not feel time passing or remember what it was before it collapsed. It simply exists, following physical laws without awareness. You, on the other hand, experience every moment from the inside. You notice warmth and cold, comfort and tension, calm and curiosity. You can imagine stars you will never see and events that happened long before you were born. That inner experience does not need cosmic size to be complete. In a universe that does not care, caring becomes something rare. Attention, awareness, and reflection are not guaranteed features of reality. They emerge only in certain places, under certain conditions. They exist here, now, in you. There is also something calming about the fact that the universe is indifferent. If it does not care, it also does not judge. There is no cosmic standard you must live up to. No expectation written into the stars. You are not late, early, successful, or failing on a universal scale. You are simply here. The magnetars continue their quiet rotation somewhere far away, storing energy, releasing it occasionally in bursts that travel across the galaxy. Those events will continue whether or not anyone is listening. Most of the universe unfolds without witnesses. And yet, sometimes, a small planet happens to be in the right place to catch a faint echo. Sometimes, a species evolves with the ability to notice that echo and wonder where it came from. That does not make the universe meaningful, but it allows meaning to exist within it. As you rest here, surrounded by conditions gentle enough to support thought and sleep, the extremes of the cosmos recede into the background. They do not disappear, but they no longer demand attention. They become part of a larger picture rather than something to confront directly. It is enough to know that they exist. Enough to know that reality extends far beyond what you can touch or see, and that your small corner of it happens to be calm tonight. That calm is not owed to you, but it is real. The universe does not need you to understand it, but understanding a little of it can change how you feel about your place within it. Knowing that magnetars exist does not make your life smaller. It gives scale to the quiet stability you are experiencing right now. Your heartbeat is steady. Your breath slows. Muscles that have been holding tension all day begin to release it. None of this requires the universe's attention or approval. It simply happens, naturally, under the same laws that govern stars and galaxies. There is a subtle comfort in realizing that you are not separate from those laws. Even though you live in a gentler expression of them, you are not an exception to the universe. You are one of its many outcomes. Somewhere far away, matter is being crushed beyond recognition. Magnetic fields are twisting space, and energy is being released in blinding bursts. Here, matter is arranged softly enough to support rest, warmth, and dreams. Both realities exist at the same time, and in this moment, you are allowed to let go of the larger one and stay with the smaller, quieter one. The vastness of the universe does not require your vigilance. It will continue on its own. You can rest. You can let your awareness narrow to the simple sensations of being supported, breathing, and slowly drifting towards sleep. The stars will continue their stories without you for a while, and when you wake, they will still be there,